So today we will discuss about the Bragg's equation. Bragg's equation. So what is Bragg equation? To study the determine the structure of the crystal structures are studied by X-ray diffraction method. So X-ray diffraction method. So in this method we will see how the X-ray diffraction method determine the crystal structure. So the wavelength of the X-ray is in the order of the wavelength. What is the wavelength? The distance between the two troughs or two crests is known as the wavelength of X-rays are in the order of interatomic distances. Interatomic distance d, small d, or interplanar distance. Interplanar distance, that is HKL. So d HKL in the crystal. Therefore diffraction is possible. So first you take the atoms are represented with the dots. So here dots are the atoms are in regular fashion, arranged in a regular fashion in crystal structure as we studied earlier. So here this is the regular fashion arrangement of the atoms. So this is the distance between the atoms, and this is the distance between the HKL planes. So this is the distance between the HKL planes. So if I join this one, this is with the atom distance will be edge length. So this will we call it as a plane. So when we impose some X-rays or on the atoms or molecules or ions or the crystal, so when it strikes to the atom and it take the diffractions, and when another ray is coming and when it touches to the atom, again it is diffracting. So the distance between these two planes is DHKL. So this is DHKL, and if I draw a line through here, then the distance is we will find out. So here this angle made by the crystal angle, that is theta. So let us assume this is A, B, and C and D. This is A, B, C, D, and this is also theta. This is the incident angle, and this is the diffracted angle. This is the reflection or diffracted angles. So that is the the waves reflected by the waves. First of all, path difference. The path difference is equals to BC plus CD. BC plus CD. And what is BC here? If you take the sine theta is equals to opposite by hypotenuse. That is opposite. What is the opposite? BC by hypotenuse is the DHKL, or that is sine theta. This is sine theta, DHKL. So BC is equals to d sin theta, d sin theta. If you see the again another angle, that is C angle sin theta is equals to opposite CD by this is the hypotenuse, that is AC is the DHKL. So CD, since it is BC by AC, so here if you say AC, that is sin theta, AC sin theta, that is D sin theta is equals to CD. So here CD is equals to D sin theta and BC is equals to D sin theta. D is the distance between the HKL planes. So here rays are coming, so ray 1 and this is ray 1, ray 2. So this is X-rays. That means there is it has some wavelength. So we will see what is the BC is equals to D sin theta plus D sin theta is equals to 2D sin theta. 2D sin theta, here if you see, this is 2D sin theta. According to Bragg, path difference is directly proportional to lambda, and path, if you remove this proportionality constant, then path difference is equal to n lambda. So if you, this is equation number 1 and this is equation number 2. If you substitute in path difference n lambda from 1 and 2, n lambda is equals to 2d sin theta, or I can write it as 2d HKL planes into sin theta is equals to n lambda. This is the equation. So here if you see the sin theta angle, sin theta is equals to n lambda by 2d HKL, or sin theta is equals to n lambda by 2a into square root of DHKL, that is h square plus k square plus l square. This is the equation for the sin theta. So if it is given the HKL planes, so if for any crystal system, for cubic lattice also, this is for cubic lattice, this is for cubic lattice, and this is for any system, this is for this equation for any crystal system, So this is the some of the terms in that Bragg's equation, that is where n is equals to order of reflections, and d is the interatomic distance, and DHKL is the interplanar distance, and if you see, theta is the incident angle, so theta is the incident or reflected angle, and this lambda is the wavelength. So this is the Bragg's equation. So next we will see what are the defects in crystals. So here we see defects in crystals. So what are the defects in crystals? Why defects in crystal? Previously we see that atoms or molecules or ions are in spherical shape. That's why if you see the spheres, there is some voids will be present in the spheres, that we call it as tetrahedral voids and octahedral voids. So due to this voids and missing of these elements or ions or molecules or atoms, then there is a formation of the defects. So in a crystal system, if if all particles are present, all particles are present, at their exact exact position, then that crystal is called a perfect or ideal crystal. Perfect or ideal crystal. But in reality, there is no perfect crystal. However, no crystals are perfect. However, in reality, no crystal structure is perfect. No crystal structure is perfect. Every crystal systems. So what is the defects in ionic compounds, ionic crystals and molecules? We'll see here. Every crystal is associated with some deviation in or imperfection. We call it as defects. The defects is in ionic crystal. Defects in ionic crystals are mainly classified into two types. What are the two types? If you see here, ionic crystal two types, that is defect in stoichiometric defects in stoichiometric compounds, in stoichiometric defects in stoichiometric compounds. Defects in stoichiometric compounds. The compounds in which stoichiometry means simple. It is number of cations and is equals to the number of anion. Then we can say the stoichiometry is balanced. So the compounds in which the ratio between number of cation to number of anion, the ratio between number of cation to number of anion is exactly equal the ratio indicated by chemical formula to the ratio indicated by chemical formula is called stoichiometric compounds. Stoichiometric compounds. So the compounds in which the ratio between the number of cation and to number of anion ratio will be exactly equal to the ratio indicated by the chemical formula is called stoichiometric compounds. Defects in stoichiometric compounds are two types. So defects in stoichiometric compounds are of two types. What are the defects in two types? Defects are, one is Schottky defect. Name itself indicates the Schottky defects. Schottky defects. This defect arises due to missing of a set of cation or anion, set of cation and anion, from lattice site, leaving behind a pair of holes, leaving behind a pair of hole. So this we call it as Schottky defect. Schottky defect is that. So Schottky defects mainly observed. Schottky defect mainly observed in ionic compounds. Mainly observed in ionic compounds with a high coordination number, high coordination and ionic compounds the size of anion and cation is nearly same. So in this let us see atoms, that is here atoms. One is cation, metal plus and X minus, metal plus and X minus. So here if you see metal plus and here metal is there, that means X minus, and here if you see metal plus and here another vacant. So this is the cation and anion. So here one cation and one anion is missing. So one anion and two anions are missing here. Again, if I draw here, if you take the anions between, so here if I draw another sphere, this will be cation, and here it is anion X minus. So X minus, and here if you take this X minus means this is metal plus. So here it is X minus is present. So one cation and one anion and one cation is missing here. So we can say it as this is a Schottky type of defect. Due to this defect, due to Schottky defect, density of the crystal will be decreases. Density decreases slightly. Why it is decreases slightly? So density is equals to mass by volume. So mass by volume it doesn't change, but mass is changing because we are removing some atoms from the lattice. So mass decreases means obviously density also decreases. This is the reason for due to Schottky defect, density decreases slightly. So how can we find out that number of Schottky defect formed per centimeter cube volume, that is volume is given by Ns is the number of Schottky defects per centimeter cube volume given by ns is equals to e to the power of, so n into e to the power of ws by r2 kt. So ws by 2 kt. From this equation we can find out the number of Schottky defects formed per centimeter cube, where n is the number of sites per centimeter cube, number of sites per centimeter cube that could be left vacant, and ws is the work necessary to create the Schottky defect, work necessary to create the defect, work necessary to form Schottky defect, Schottky defect. This is the ws, and k we know that Boltzmann constant, r by Avogadro's number, that is Boltzmann constant, and T is that absolute temperature. So this is about the Schottky defects. Next we will see what is the Frankel defects. So again stoichiometric defect is second type is Frankel defect. So Frankel defect, if you see the Frankel defect, this defect arises due to missing of an ion from its correct lattice and occupies the interstitial position. So this defect arises due to missing of an ion from its correct lattice and occupies interstitial or vacant position. Interstitial position. So interstitial position, Frankel defect. So here Frankel defect is mainly observed in ionic compound. So in ionic compounds with low coordination number is a number which neighboring atoms were present with the central atom, that is coordination number. And ionic compound where the size of anion and cation differ largely. What is that mean? The cation and anion sizes differ largely, then we find this type of defects. Those defects we call it as Frankel defect.